Hello everyone, welcome to Rasaayana Institute of Sciences. In this video, we will discuss about what is inductive effect and what are the general characteristics of inductive effect in organic molecules. So generally inductive effect we can define like this. I am saying inductive effect is a permanent effect. It is a permanent effect operated in polar covalent bond. So this effect is most commonly observed in polar covalent bond only. It is a permanent effect operated in polar covalent bond. So what is the meaning of permanent effect? Permanent effect is nothing but this is the effect responsible for displacement of electron density from one atom to other atom without using any reagent. So without using any reagent is called permanent effect, with reagent is called temporary effect. So then what is actually the meaning of permanent effect with respect to polar covalent bond? Especially inductive effect is nothing but induction of permanent dipoles in polar molecule, otherwise we can say polar covalent molecule. So molecule is already polar, with the help of that there is a permanent dipoles are going to be created. Permanent dipoles nothing but partial negative, partial positive. So here I can say the permanent dipole, here we can say partial negative charge. Partial negative will be represented like this. Partial negative and partial positive charge is going to be generated. Partial positive. Partial positive is represented by delta plus like this. So by generating partial negative, partial positive, that is nothing but a permanent dipoles within the covalent bond. So this partial negative, partial positive is going to be generated between two atoms. The two atoms should carry two atoms with unequal electronegativity. Unequal electronegativity. If two bonded atoms having unequal electronegativity, then this partial positive, partial negative charge will be distributed between the two atoms. So the key factor is, suppose if I take hydrogen and here this is chlorine. Now generally chlorine is a more electronegative element. The shared pair of electron is moving very close to chlorine and that chlorine carry negative charge, hydrogen carry partial positive charge. So this is a permanent dipole. Now inductive effect is present in hydrochloric acid. It is same way I can write a methyl chloride. Now carbon chlorine bond is present. Now shared pair of electron very close to chlorine. Whichever side that shared pair of electron is going on, that side you will get partial negative charge. And here whichever is losing that electron density, that becomes partial positive. So here I can also write hydroxy group. Here shared pair of electron is present. Oxygen is more electronegative, that can withdraw electrons more from carbon. So on that time carbon carry partial positive, oxygen carry partial negative. So like that we can take any high electronegative element. On the time there is a generation of a partial positive, partial negative, that is nothing but permanent effect. Also called permanent dipoles. They are called permanent dipole. That value never changes. It is always permanent without using any reagent. So indirectly I am saying this share pair of electron is moving very close to oxygen or high electronegative element. Okay. So that is generally nothing but a inductive effect. How much this shared pair of electron is moving very close to high electronegative element, based on that the dipoles will be generated. So sometimes it is higher negative, higher positive. Suppose if it is a more electronegative element, more negative, more positive is observed. Okay. Then generally it is operated in sigma bond only. Inductive effect is an effect which is operated only in sigma bond. It is not operated in pi bond as well as non-bonding. If it is operated in sigma bond, only inductive effect. If it is operated in pi bond, that is mesomeric effect. Okay. So inductive effect is generally represented by an arrow midway between two bonded atoms. So this symbol indicates that electron density moving from less electronegative element to high electronegative element. Okay. So generally you can represent like this. Suppose methyl and chlorine are get connected. Chlorine is a more electronegative element, carbon is less electronegative element. Now I am showing that arrow is towards chlorine side, which indicates chlorine is accepting the electron density, carbon is losing electron density. So which means the electron density especially the shared pair of electron moving very close to high electronegative element. So that is actually inductive effect indicates. Okay, so we are not transferring these electrons on chlorine, just this lone pair of electron very close to high electronegative element. So indirectly I am saying that this is called drift of shared pair of electron. So the drift of shared pair of electrons towards high electronegative element is nothing but a inductive effect. So simply remember, if I write a arrow between two atoms, this arrow indicates that electron density or electrons are moving very close to high electronegative element. But remember, we are not transferring complete electrons to high electronegative element. Means these two electrons never completely added on chlorine. So means we are confirming that inductive effect is not a ionization effect. It is only a transferring electron density from less electronegative element to high electronegative element. Okay, so some elements are there in which two atoms are unequal, but they don't have proper induction. So especially see, if I take hydrogen and hydrogen, in this case shared pair of electron is exactly middle of the bond, so there is no inductive effect. Okay, and if I take carbon hydrogen bond, carbon hydrogen, carbon hydrogen, in this case also almost all shared pair of electron exactly middle, there is no inductive effect. Okay, then I can take carbon carbon bonds even. In this case, shared pair of electron between these two is exactly middle. So I can say there is no net dipoles are going to be created within this molecule. There is no inductive effect operated in these molecules. So this is called symmetric molecules. This is symmetric molecules. When you take any symmetric molecule, there is no inductive effect is operated because the shared pair of electron exactly present middle of the covalent bond. So on that time there is no polarity, these molecules are non-polar. Mostly if molecule is non-polar, there is no inductive effect. Inductive effect, blindly remember, it is operated through sigma bond only. Okay, then suppose if any molecule having a set of carbons and one element is high electronegative, now it is a withdrawing electron, electron density is keep moving from one carbon to other carbon. Now here it is a partial positive, and here it is partial positive like this. Now this carry partial negative. Remember, inductive effect is depends upon the distance. It is a distance factor. Okay, as distance increases, inductive effect decreases. Okay, so as distance increases, inductive effect decreases. So maximum, whenever if it is connected in a straight chain, maximum it is applicable up to 3 carbons. It is applicable up to 3 or first 3 carbons. First 3 carbons this inductive effect is operated, and especially first carbon maximum effect will be there, second carbon, and almost all it is not easy to measure from fourth carbon. So first 2 carbons are rapidly affected by inductive effect group. So later on third carbon or third atom carry little bit less effect, and from fourth carbon onwards this effect is permanently not applicable. So we are drifting the shared pair of electron through covalent bond. If this chlorine is withdrawing electron, it will take much more electron density from this carbon, single bond, later on this carbon and this carbon. So that's why I am saying that inductive effect is a distance factor, which means it is depends upon the distance. Means maximum 2 carbons you can apply, very little effect will be there on third carbon. Almost all it is negligible from fourth carbon. See, when if it is withdrawing electron density, effect is very high on this one. Later on this, very small effect will be there. So very small, nothing but write down more delta numbers. Okay, so inductive effect is not A. It is not complete transfer of electrons. It is not complete transfer of electrons. Don't think that electrons are completely transferred to high electronegative element. Okay, so here electron density shifted to chlorine. Okay, this is inductive effect here, and but this is not a inductive effect. If you make them into ionize, this is not inductive effect here. So simply remember, the shared pair of electron present on chlorine only, very closer to chlorine, but hydrogen never loses its own electron. So when shared pair of electron moving very close to chlorine, then there is a generation of a high electronegative, partial negative, then this hydrogen losing electron density, that is partial positive. So finally we can say that it is a A permanent effect which is generates a dipole on two atoms, but there is no transfer of complete electrons to high electronegative element. If they transfer, that is called ionization, but that is not inductive effect. Okay. So generally, inductive effects classified into two types. Two types of inductive effect groups are present. First one, plus inductive effect group, and one more is minus inductive effect group. Plus inductive effect group is nothing but the groups which can release electron releasing groups. So a reference atom is hydrogen. If you compare with hydrogen, all these atoms are electron releasing groups through sigma bond only. So if I take best example S minus, then followed by NH minus, and then O minus, then we can also compare like this: C double bond O, S minus, C double bond NH minus, and C double bond O. Then followed by tertiary butyl. So 3 methyl groups are present here around this carbon. This is tertiary butyl. Then secondary isopropyl. Then followed by ethyl. Then go for methyl, and at last it will be hydrogen. So these are the order of electron density donating groups. So if any sigma bond connected by S minus, NH minus, O minus, which indicates these groups are regularly giving electrons to corresponding atom. Okay, so the such groups are called plus inductive effect. This effect is operate only through sigma bond only. Okay, so it is connected to any atom means with sigma bond only. There is no mesomeric effect in this one. Next, second case, minus inductive effect groups. Minus inductive effect groups are nothing but electron withdrawing groups. Electron withdrawing groups, nothing but the groups which can withdraw electron through sigma bond. Okay, so a reference atom is which is better than hydrogen. So whatever groups are present, that groups are available, and they are keep on withdrawing electron density through sigma bond. That is called minus inductive effect. So especially here I can write ammonium. NH3 attaches to any sigma bond. It is a withdrawing group. Now then nitro, here cyano, then sulfonic acid SO3H, then go through aldehyde. This is aldehyde group, and this is ketone, and here it is acid, then acid halide. Then after that you can go for fluorine, chlorine, bromine, iodine. Okay, then go through hydroxy, alkoxy, then even amine group, and go through carbon-carbon triple bond, then benzene, then finally double bond, carbon-carbon double bond, and at last hydrogen. So if these groups are available anywhere else, these groups are generally indicates that they are withdrawing electrons through covalent bond. Covalent bond nothing but sigma bond. So two covalent bonds are there, sigma and pi. Now these particular groups always withdraw electrons through covalent bond only. Okay, so they are called minus IE group. These groups withdraw electrons, and if you take these groups, plus I group, these groups can regularly donate electron through covalent bond. Okay, so now see the factors. In short, I will explain the factors so that you will get some idea. So what are the factors affecting on inductive effect? Factors. Okay, first factor, it is going to explain stability of carbocation. Stability of carbocation. Okay, if any carbocation is taken with any electron releasing group, stability increases. Suppose see, carbocation bearing generally positive charge. So if carbocation bearing positive charge, all hydrogens are neutral. This cation already deficient, so it is unstable. Suppose if I substitute one methyl group here, already carbon bearing positive charge is unstable, having less electron density. But when methyl is connected, methyl is a releasing group that can release some electron density to this carbocation, it becomes stable. Okay, then I can take one more example. Here see, I am writing two donors here. Two donors can release 2 electron density. As number of electron donating groups are increasing, stability of carbocation is regularly increases. See here. Now this carbon is suffering from electron density. Now one group is releasing electron. Here 2 groups are releasing electron through covalent bond. Now 3 groups are releasing electrons to covalent bond. So I can say this is super primary, primary carbocation, secondary carbocation, and this is tertiary. As number of donors increases, stability also increases. Okay, so I can say that tertiary is more stable than secondary, secondary is more stable than primary, and then super primary. So this is key reason for showing the stability of tertiary very higher as compared to secondary as well as primary. Because methyl is a releasing group through covalent bond, 3 donors are there, this is found to be stable. Okay, and if I take any electron withdrawing group, see I am writing nitro as an electron withdrawing group, CH2 plus, and I am writing 2 electron withdrawing groups, here hydrogen and this is plus, and I am writing 3 electron withdrawing groups, nitro, nitro and one more nitro. So if you see this, nitro is a withdrawing group, it can decrease electron density, 2 withdrawing groups are there, 3 withdrawing groups are present. Now on this case if you observe clearly, as withdrawing groups are increasing, stability decreases. Already suffering from lack of electron density. Electrons density is very less. On the time if you substitute any electron withdrawing group, density further decreases. So already unstable, little more unstable, highly unstable, and this is one of the most highly reactive species because 3 withdrawing groups are present so that it can be highly unstable. So I can say first one is less stable, first one is more stable than second one is more stable than third one, and then fourth one. Okay, so indirectly I am saying that carbocation stabilized by plus IE groups, this is plus IE groups, and they are stabilized by destabilized by minus IE groups. Plus IE groups will increase the stability of cation, minus IE groups will decrease the stability of cation. Say as number of withdrawing groups increases or minus IE groups increases, stability becomes very less. Okay, next. So it can also explain stability of carbanion. Stability of carbanion. So what is carbanion? Carbon bearing negative charge is called carbanion. Carbanion nothing but carbon having excess electron density already. Already this carbon having more electron density. Now I am substituting a electron releasing group here. So if I take these 2 species, here this is CH3 negative, and here I am taking a carbanion with negative charge. Now 3 donors are present, and here 2 donors are present, here 1 donor. Already this carbon carry more electron density. Due to presence of donating group, stability is very less because already they have excess and this group is giving somewhat more extra electron density, then stability decreases. I can say first one is more stable than second one, then third one, and then fourth one. So I can say clearly plus IE group plus inductive group decrease the stability of carbanion. Now if I take carbanion with electron withdrawing groups, this is CH2 and here 1 withdrawing group, and this is CH NO2, 2 withdrawing groups I am writing with negative, and I am writing carbon with 3 withdrawing groups, NO2 taken 3 times. Now as number of withdrawing groups increases, sharing partners are increases, stability also increases. So carbanion gets stabilized by electron withdrawing group. So as number of withdrawing groups increases, stability also increases. I can say fourth one is more stable than third one, and then second one and first one. So stronger the withdrawing group, stronger the stability. Okay, suppose if I take a carbanion, carbanion attaches to nitro, then carbanion attaches to cyano, then carbanion attaches to carbonyl group here, C double bond OH. Now nitro is a strong withdrawing group as compared to cyano. Cyano is a strong withdrawing group as compared to aldehyde. So I can say that greater the strength of minus IE, greater the stability. I can say first one is more stable than second and then third. Okay. Suppose if carbanion attaches to aldehyde and ketone, right? See, this is aldehyde. Aldehyde is a strongest withdrawing group. Then ketone. This is ketonic alpha carbon. Then I am taking a acid alpha carbon. If carbanion very close to aldehyde, carbanion very close to ketone, carbanion very close to acid. See, this is more deficient. It is a powerful withdrawing group as compared to ketone because ketone having 1 donor. And here hydroxy, here it is a mesomeric factor. This lone pair will stabilize this carbon, so withdrawing capacity is very poor. So I can say greater the withdrawing capacity, greater the stability. See the order what I given. So based on that, I can say first one is more stable than second, second one is more stable than third one. That is the order of stability for carbanion. Okay. Then go through stability of free radical. Stability of free radical. This factor effectively explained in hyperconjugation. Right now, I can explain only one example because this is similar to carbocation. It is a 7 electron species free radical. So 7 electrons nothing but electron deficient. Electron deficient nothing but lack of electron density, short of electron density. So when any species having short of electron density, it is get stabilized by releasing groups only. Here hydrogen, here radical, it can release electrons. Now here hydrogen, methyl, and here one more methyl, and this is the one where radical is connected directly to carbon. Now it is short of electron density, 1 methyl, 1 releasing group, 2 methyl, 2 releasing group, 3 methyl, 3 releasing group. So I can say that similar to carbocation, fourth one is more stable than third, and this is second and then one. Remember, free radical stability effectively explained in hyperconjugation only. In case of inductive effect, there is no proper evidence. So we can explain roughly based on short of electron density, but completely you will understand only in hyperconjugation. But roughly you can say that 7 electrons are present. 1, 2, 3, 4, 5, 6, 7. So generally 8 electrons are stable but becomes unstable due to lack of 1 electron. So due to 1 electron deficiency, methyl can release some electron density, 2 methyls can release somewhat more extra electron density followed by this one. So as releasing groups increases, stability also increases. Suppose if I substitute any withdrawing groups over here, it is quite opposite, similar to this one, carbocation. So here one withdrawing group I written, then 2 withdrawing groups I am writing, NO2, CH radical, then 3 withdrawing groups I am writing, NO2. Okay, so I can say that first one is more stable than second one is more stable than third one. Okay, first one, second one, third one, and finally fourth one. That is stability order for a free radical. Free radical stability almost all equal to carbocation stability. Okay, next go through fourth stability factor, reactivity of alkyl halide. Reactivity of alkyl halide. This is most important one. You can expect one complete chapter belongs to alkyl halide. In that one, maximum factors are depends upon the inductive groups only. So generally alkyl halide nothing but Rx. X may be any kind of halogen. Now this reactivity depends upon the carbocation stability. Okay, so after breaking this bond, now see, this is found to be stable. Suppose if carbocation is stable, this bond is unstable, means molecule is highly reactive. Unstable nothing but highly reactive. If you are breaking this bond very easily, means it is giving a stable cation. If they give stable cation, we can break them very easily, it becomes unstable. Unstable nothing but reactive, highly reactive. Now second possibility, if I take Rx, R is removed in terms of cation, X is in the form of X minus by transferring like this. Now I am saying that already original molecule is stable. It is stable. Stable means less reactive. It is less reactive because it is giving a unstable cation. Unstable cation. If it is unstable, bond is very stronger. If cation is unstable, the formed cation is unstable, this bond is very stronger. If it is very stronger, not easy to break, less reactive. If cation is stable, bond is weak. So we can break them very easily if it is unstable. So remember, reactivity of alkyl halide always depends upon the formed carbocation stability. If it is forming a stable carbocation, it is giving a unstable alkyl halide. Okay. So if I take one of the example regarding tertiary alkyl halide, see this. Tertiary alkyl halide, here I am writing a bromine. So then I am writing secondary CH3 and here it is bromine. Then I am writing a primary CH2Br. Now I want to write reactivity order of these three. So which among the following is more reactive, means it is depends upon the form of carbocation after breaking. See this, if you remove this after breaking, you will get a stable carbocation. If carbocation is more stable, if this is more stable, this bond is very weak. Means we can break carbon halogen bond very easily if it is a tertiary, because tertiary carbocation is more stable. Okay, later on you will get secondary. Here hydrogen CH3 plus, then here hydrocarbon CH3 CH2 plus, like this. Okay, so this is more stable, later on this one, later on this one. If this is more stable, this is more reactive. I can say that tertiary alkyl halide is more reactive as compared to secondary alkyl halide. Secondary alkyl halide is more reactive as compared to primary alkyl halide. So this is reactivity order. This is a complete reactivity order. Okay, so reactivity order, if you concern, tertiary is more reactive because tertiary is giving tertiary carbocation, followed by secondary, followed by primary. Suppose we know one halogen is attached to 3 different groups here. Here I am writing nitro, then I am writing cyano, and here bromine is present, then I am writing aldehyde group. Now can you say which bond can be broken very easily? See, on this particular case, if you want to say the reactivity order, first you remove halogens and think about cation stability in your mind. Which is most stable cation, that is more reactive after removing halogen. Suppose see, if I remove here, you will get one cation, cation, cation after removing bromine. This cation destabilized by nitro. Nitro is a powerful withdrawing group, followed by cyano and aldehyde. So this is little bit better because it is a weak withdrawing group. Cation is little bit stable. So I can say third one is more reactive, then second one, and then first one. This is reactivity order. Electron donating group increase stability of cation. If electron donating groups is present, it is more reactive. So it is related to primary carbocation, secondary carbocation, tertiary carbocation stability order only. Okay, so that is fourth factor. And fifth factor, acidity of alcohols. Alcohol's acidity. Okay, so if any molecule acidity, if you want to explain, it is depends upon the conjugate base. See, this is a conjugate base of this one. Okay, alcohol is nothing but ROH. If you remove this proton, forms a alkoxide ion. This is alkoxide ion. As stability of alkoxide ion increases, acidity increases. So which means already anion is there, this group is releasing electron. So I can say that electron releasing groups decrease acidity, and electron withdrawing groups increases acidity of alcohol. Okay, if it is a strong releasing group, less acidic because it is unstable. Alcohol acidity depends upon this stability. If alkoxide ion is more stable, this is more acidic. So based on that, I can say that methanol is more acidic than ethyl alcohol. Okay, ethyl alcohol is more acidic than isopropyl alcohol. Isopropyl alcohol is more acidic than tertiary butyl alcohol. So that is the order. Okay, so we can explain this acidity of corresponding alcohols like that. So primary is more acidic than secondary, secondary is more acidic than tertiary. Okay, remember acidity of alcohol depends upon stability of conjugate base. Conjugate base of alcohol is called alkoxide ion. If this alkoxide ion is stable, this is more acidic. Okay, in the same way we can also explain acidity of acids. Carboxylic acid. Okay, so inductive effect also explain acidity of carboxylic acid. Carboxylic acid acidity, see this, RC double bond OH, if they loses proton, forms a carboxyl ion, RO minus and here H plus. So what is the role of R? It is a releasing group. Now see, if it is a releasing group, this is found to be unstable. Releasing group decrease acidity. So based on this, we can say this is carboxyl ion. So similarly, if I substitute methyl, ethyl like this, then this stability becomes unstable. This is unstable. This stability becomes unstable, I am saying. So if this is stable, this is more acidic. Here we need to substitute a group which is withdrawing. If I substitute a withdrawing group over here, R, if R is a withdrawing group, this is stable. If this is stable, this is more acidic. So almost all same points. Separately, you will see more number of applications in case of carboxylic acid. If you know inductive and mesomeric clearly, you will understand carboxylic acid acidity. But only one point to remember, in these two cases, electron releasing group decrease acidity, withdrawing group increase acidity. And the last factor, okay, basicity of amines. Basicity of amines. Amines basicity can be explained by ability of donating lone pair of electron. Suppose if this lone pair is donated to any acid, then there is a formation of ammonium, alkyl ammonium. This is called conjugate acid. This is conjugate acid. If conjugate acid stability increases, basicity increases. Basicity nothing but ability of donating lone pair of electron. If this is donating more effectively, more basic. If lone pair is more available for any acid, it is more basic. This is available only when if R is a releasing group. So it is quite opposite to above statement. Electron releasing groups increases basicity. Then what about electron withdrawing groups? Electron withdrawing group decreases basicity of amines. So basicity of amines depends upon the nature of substitutions. If it is a strong donating group, more basic. If it is a weak donating group, less basic. If it is a powerful withdrawing group, it is not a basic in nature. Acidity depends on stability of conjugate base. Basicity depends on stability of conjugate acid. Because if cation is stabilized by donor, basicity of any nitrogen with donor, basicity increases. Okay, so that is about inductive effect and their applications. Okay, so make a short revision. See this, what is inductive effect? It is a permanent effect operated in polar covalent bond, is nothing but a inductive effect. So induction of permanent poles in a polar covalent bond is called inductive effect. So permanent poles nothing but partial positive, partial negative, like this. Writing like this is called permanent pole. So this is possible when these two atoms are unequal electronegative elements. So generally we can write partial negative, partial positive only when if this lone pair of electron is drifting towards high electronegative atom side. So it is operated in single bonds only. It is represented by a arrow midway between two bonded atoms. Then later on, if any bonded atom shared pair of electron is oriented in exactly middle of the bond, on that time they are symmetric molecule, there is no inductive effect. Okay, carbon hydrogen, there is no inductive effect. So inductive effect depends upon the distance. As distance increases, inductive effect is decreases. Especially inductive effect is operated up to first two carbons. So third carbon, infinitesimally very small effect will be there. From fourth carbon onwards, it is almost all negligible. So if it is a donating group or withdrawing group, this effect will be there up to 3 carbons maximum. Okay, almost all it is not easy to find inductive effect from fourth carbon onwards. So that's why I'm saying it is distance factor. As distance increases, inductive effect decreases. It may be a donating character or withdrawing character. Okay, so mostly it is observed in first 3 carbons only. So generally remember, generally people will think that high electronegative element is taking that electron density and it is completely removed off from the molecule. That is not acceptable. High electronegative element will take out that electron density more towards itself but not ionizable. If it is ionizable, that is not a inductive effect. Generally 2 types inductive effects are present. Plus inductive, we are releasing groups. Minus inductive, they are withdrawing groups. These all are withdrawing groups, are their order also given. What are the factors related to inductive effect? Remember, inductive effect related to sigma bond only. If you remember sigma bond and factors affecting on sigma bond, that is inductive effect. Okay, stability of carbocation. Carbocation stability explained by inductive effect clearly. Donors increase stability of cation, withdrawing groups decrease stability of carbocation, because carbocation is electron deficient species or electron deficient molecule. First thing you need to know what type of molecule it is. Okay, so they don't have electron density, that's why the groups which can release electron density, it becomes more stable. Right? Next, go through this one. Carbanion, already they have more electron density. If these groups are giving somewhat more electron density, unstable. So on that time take electron withdrawing group that can increase the stability. Even radical also remains same. Radicals are unstable, stabilized by donors, destabilized by withdrawing groups. Next, go for alkyl halide reactivity. So if you know this point, selective carbon halogen dissociations you can understand clearly. Alkyl halide reactivity depends on carbocation stability after bond dissociation. If cation is more stable, this is more reactive. If it is unstable, less reactive. So we know this cation, tertiary is more stable than secondary, secondary carbocation more stable than primary. More stable carbocation after ionization will give more reactive alkyl halide. So tertiary is more reactive than secondary and primary. Here also same. Then finally, acidity depends upon stability of conjugate base. After forming a conjugate base, if it is stable, this is more acidic. So we know that they carry more electron density. If this group release electron density, it becomes unstable. So I can say releasing group decrease acidity, withdrawing group increase acidity. So almost all same point regarding carboxylic acid. And in case of amines, ability of donating lone pair of electron. How much easily a molecule can donate its lone pair of electron to acid, that is called basicity. If it is releasing or donating very easily, this is more basic. So they can donate only when if they carry releasing groups. So I can say releasing groups increase basicity, withdrawing group decrease basicity. Okay, so that is about few factors. With rough examples I explained, but in-depth analysis is required, especially for IIT mains and advanced. It is only a conceptual knowledge. Applicative knowledge on individually we will discuss with individual heading by putting a acidity of carboxylic acid. Many examples I will explain, but it is a major factor I am explaining. What is major reason for showing acidity? That I explain. Every time conjugate base, conjugate acid, regarding acids and bases, if you find clearly, then only corresponding acidity and basicity you can explain. Okay, so that is about this video. Hope you people will understand. Try to subscribe our channel so that you will get all new videos and updated videos regularly in your YouTube channel, so that you can get that notifications as well as possible, and you can recollect the concepts and you can rectify the doubts regarding to the concepts, and you can prepare for your examination clearly. Okay, thank you for watching this. Thank you for supporting us.